Hi! In the previous section you have seen that any linear transformation is a matrix transformation. To be precise, if T is a linear transformation from Rn to Rm, then there is a unique matrix A such that T of x is equal to A times x for all vectors x in Rn. The matrix A is called the standard matrix of the transformation. This result means that operations on linear transformations can be translated to operations on matrices. In this video, I will show you how this works out for composition of linear transformations. So what do I mean by composition? Well, suppose that T1 is a linear transformation from Rn to Rm and T2 a linear transformation from Rm to Rk. Then we can combine T1 and T2 into a new transformation, T3, from Rn to Rk, as follows. Take an x in Rn, apply T1, and then apply T2. We call T3 the composition of T1 and T2. Composition is often denoted with a small circle. So what can we say about T3? The main result of this video is the following. If T1 is a linear transformation from Rn to Rm and T2 a linear transformation from Rm to Rk with standard matrices A1 and A2 respectively, then the composition, T3, is also a linear transformation and its standard matrix is equal to the product of A2 and A1. Recall that matrix multiplication is not commutative in general, so mind the order here. The standard matrix of the linear transformation that you apply first is to the right, and the standard matrix of the second transformation is to the left. I will illustrate the theorem with an example later in the video, but first I would like to show you why it is true. By definition, applying T3 to vector x is the same as first applying T1 to x and then T2 to the result. Using the standard matrices of T1 and T2, we can translate this to matrix multiplication. First multiply x with A1 and then multiply the resulting vector with A2. Make sure that you multiply from the left. Now comes the central point. Matrix multiplication is associative, which means that it does not matter how you put the brackets. Indeed, by associativity, we could also first calculate A2 times A1 and then multiply the result with vector x. This may seem trivial, but actually it's not. It takes some effort to show that matrix multiplication is associative. You can find the proof in the first week of the course. We find that T3 is a matrix transformation, hence a linear transformation, and the standard matrix is A2 times A1. This concludes the proof. I'd like to end with an example to illustrate the theorem. Consider the rotation in the plane around the origin counterclockwise by an angle alpha. This is a linear transformation with this standard matrix. Now suppose we apply rotation again. We then have a composition of two rotations by angle alpha. The theorem tells us that this composition is again a linear transformation, and indeed it is a rotation by angle 2 times alpha, which has this standard matrix. On the other hand, the theorem tells us that the standard matrix of the composition is equal to the product of the standard matrices of the two rotations. That is, equal to R alpha times R alpha. We can compute the product. Check it yourself. Now these two matrices should be equal. Are they? Look at the diagonal elements. If you recall the double angle formula for the cosine, you see that the diagonal elements are indeed equal. Similarly, the off-diagonal elements are equal by the double angle formula for the sine. You see that the theorem relates a geometric point of view, namely composition of rotations, to an algebraic point of view, namely multiplication of matrices. Both points of view have their advantages and disadvantages. The theorem enables you to move from one to another, and as a bonus, in this example, you can re-obtain the double angle formulas for the sine and the cosine, if you have trouble remembering them. You can explore the theorem yourself in the exercises.